Yesterday I reminded you of 3 equations that you learned last year in Physics 20. The first one was for gravitational force, Gm1 m2 over r squared. There's a rough equivalent to that equation for electric force. What is it? Coulomb's law. What's the equation? F is equal to kq1 q2 over r squared. Talk about similarities and differences again here. Okay, similarities, the structure of the equation. They're both what we call inverse square relationships. Why are they called inverse square relationships? Where does that term come from? Inverse square. Okay, so divided by something. And square means obviously the square of the distance, right? So it's divided by the square of the distance that separates them. So they're both inverse square relationships. The structure of the equation is identical. Now, of course, there's variables that are a little bit different. One of the things that's different about these 2 equations is the relative strength of the forces. Which one's a bigger force? All other things being equal, which one's a bigger force? Alan? Yeah, the Coulomb force is bigger. We know that for a number of reasons, but the most obvious reason is this, right? The constant. G is 6.67 times 10 to the minus 11. K is 8.99 times 10 to the positive 9. Okay, you compare those 2 numbers. K is 10 to the 20 times bigger than G. That's going to give us a bigger force, a much bigger force of electrostatic attraction or repulsion than gravitational attraction. The final thing that we differentiate these 2 equations with is the direction of the force. Gravitational force is always an attractive force, whereas the electric force can be attractive or repulsive. The next equation we looked at from yesterday was the gravitational field equation. Now, we looked at 2 of them, in fact. The gravitational field equation number 1 and the gravitational field equation number 2. What's the difference between number 1 and number 2? Producer versus experiencer. In other words, if you have information about what's causing the field, then you're going to use the producer equation. If you have information about what feels the field or experiences the field, you're going to use the experiencer equation. Okay, right now, the Earth is the producer for us. It's causing the gravitational field of 9.81 meters per second squared. Okay, right now, we are the experiencers. If we have information about the Earth, let's use the producer equation. If we have information about you, let's use the experiencer equation. Now, which one's which? Okay, one's producer, one's experiencer. Equation number 1, producer, experiencer. John? Equation number 1, producer, experiencer. Good. Yeah, it's the producer one. Here's the rule of thumb. If you're trying to find the field strength a certain distance away from the mass, in other words, look, you got the mass of the Earth. What's the field strength a certain distance away from the Earth? Then that object is going to be the producer. If you're trying to find the field strength where the object is, then that object is experiencing the field. I want to find the field strength right there where that pen is right now that I'm holding up in my hand. I want to find the field strength right there. Well, that pen isn't causing the field where it is. The pen is experiencing the field where it is. Okay, if I want to find the field strength 100 meters from the surface of the Earth, okay, then the Earth isn't experiencing the field 100 meters from its surface. The Earth is producing the field 100 meters from its surface. So the rule of thumb is, look, if you got an R, if you got a distance that separates it, okay, then it's going to be a producer. Okay, that's the rule of thumb. If you've got an R, then it's going to be a producer. Hey, what if you've got data about both the producer and the experiencer? What if we have data about the Earth that causes the field right there where Brett is, and then what if we have information about Brett that's experiencing the field right there where Brett is? Which one do I use? Doesn't matter, whichever one you want. I'd probably use the last one because it's a little bit easier, right? It's a little bit easier mathematically, but it doesn't matter. You should get the same value because the field that he experiences is going to be exactly the same as the field that the Earth produces, right? He's got to experience it, the field that's caused by something, right? Caused by the Earth. What's the rough equivalent to the gravitational field producer equation? The rough the electrical equivalent to that. The electric field is equal to KQ over R squared. I'm missing a couple things here. What am I missing? Yep. The vector sign, and that's the most important thing, right? The other one is the absolute value signs that, you know, we can choose to overlook that. If you forget to put the absolute value signs in, but I'm not going to overlook putting the vector sign in. You will make a mistake if you don't put the vector sign over it. You will. Each and every one of you, at some point this year, are going to get that mixed up with energy if you don't put the vector sign over it. You might still get it mixed up with energy at some point, but you're less likely to if you remind yourself that it's different from energy by putting the vector sign in there. The electric field experienced by a charge, E is equal to F over Q. What does Q stand for in the first equation right here? Charge of the producer, right. What does Q stand for in the second equation? Charge of the experiencer, good. We had a couple questions for homework on page 549, and I had a request to go over question number 1, I think it was. Number 1. Anybody for number 2, or is that one okay? All right. Number 1 says the electric field at a position 2 centimeters from a charge is 40 newtons per coulomb. Right away, which am I dealing with here? A producer or an equation? Sorry, a producer or an experiencer? I'm trying to find a field strength, or I have the value of the field strength, a certain distance from a charge. Is that charge, whatever the value of that charge is it producing or experiencing? It's producing, right? Okay, if there was a charge at that point that you had data about, that would be the experiencer. So it is a producer. If I recognize that right away, it might be a good idea just to write that down. Okay, just so I don't forget if the question becomes a little bit wordy later on. Okay, what I do want to do is circle that 2 centimeters because that's a non-standard unit and I got to remember to convert that. Okay, this is going to give me a distance. This is an electric field. Don't forget the vector sign over it. I want to find the charge. This is going to be the charge of the producer, right? So let's use my producer equation. E is equal to KQ over R squared. Solving for Q, let's take the R up by multiplying. The R squared up by multiplying. Let's take the K down by dividing. And Q ends up being equal to E, which is 40 newtons per coulomb, times R squared, 0.020 squared. Travis, I think it was you yesterday or a couple of days ago, that was having an issue with, I think it was millicoulombs. Was that you? Okay. And we said, look, lots of us have a little bit of trouble with that, right? Lots of us have a little bit of trouble with, okay, is it 0.2 or is it 0.02 or is it 0.002? We get mixed up with that. Okay, if in doubt, hey, as long as you know the conversion factor, just punch it into your calculator. Okay, 2 divided by 100 gives me 0.02. Okay, if you're susceptible to making that mistake, pull out the calculator every time. So K is 8.99 times 10 to the 9. We do the math on that one, and I think it should work out to be 1.78 times 10 to the negative 12 coulombs. Now, this equation won't tell me whether it's a positive or negative charge. They're telling me that it's positive in my answer here. So how do we know that it's a positive charge if the equation won't give me the fact that it's a positive charge? The equation only gives me the magnitude. Right? It says positive right there. Okay, but that doesn't mean it's a positive charge just because that's what I got. Right? Equations don't tell me negative or positive charge. How do I know it's a positive charge? Brett? Good. It's directed away from the producer. So if you have a producer and the field is pointing away from it, what do you know about that producer? It's got to be positive, right? Does that make sense, guys? So it came out mathematically to be positive, coincidence. Okay, we know that it is a positive charge, not because it came out mathematically to be that, but because, as Brett said, it's pointing away from the producer. All right. What about this one? Let's try this one. Here's a new one. 11.3 on page 550. 2 positively charged spheres, A and B, with charges of 1.5 times 10 to the negative 6 and 2.0 times 10 to the negative 6 are 3.3 meters apart, times 10 to the minus 2 meters apart. What's the electric field midway in between them? I don't know about you, but when I see this question, it kind of rings a bell a little bit. What does this remind you of a little bit? For me, it reminds me of those Coulomb's law questions where we have 3 charges. although we only have 2 charges here, it's going to be almost the same thing. Okay, remember those Coulomb's law problems where we had a quiz on that the other day, right? Okay, 3 charges, you had to draw a free body diagram, you had to calculate each of the charges, the forces, sorry, and then you had to add up the forces. Remember those? I hope you do. This is almost the same, except we're not dealing with forces here, we're dealing with fields. Both of these are producers. Both of these cause a field at point P, right? Point P isn't where the charge is, so these charges that we have information about have to be the producers. They both produce a field at point P. Let's figure out what direction both of those fields are. Let's calculate both of those fields, and then let's add them up. Maybe we have to make 1 or 2 of them negative, but let's add them up vectorially. All right. Charge A is positive. Forget charge B. It doesn't exist. Okay, pretend it's not there. Charge A is positive. Which way does the field point surrounding a positive producer? Away from it. So the field right up here would be upwards. Here it would be downwards. Here it would be to the right, caused by A. Now, I don't care about this one or this one, because I'm trying to find the field strength midway between, not above and below. Okay, but the field is, anywhere you look at it, is going to be away from the positive producer. So, we got the first one. Let's take a look at the second one now. The field caused by positive producer B is which way? Toward or away? Sorry? Toward it? No. Nick? It's going to be away from it. Right? Pretend the rest of it isn't there. The field caused by B is going to be away from it because it's positive. Okay, we don't care about these ones because we're not trying to find the field strength there. Look, I got 2 fields here. One's pointing to the right and one's pointing to the left. When you're trying to determine which way the field points caused by A and B, just pretend the other one isn't there. Look at it if it's a positive or a negative. It's either away from it or towards it. Let's get the values of both of these fields here now. Let's say EA is equal to KQA over R squared. QA is 1.5 times 10 to the minus 6. And what's R? 3.3 times 10 to the minus 2? Divided by 2, right? Because we're trying to find the field strength midway between, right? That's going to be 1.65 times 10 to the minus 2. Listen, if you think there's any chance of making a mistake with dividing by 2 there, use your calculator. I remember one time I did this question, and I made it just a stupid mistake, but it happens, right? I made it 1.05. 1.05. No, sorry, I made it 1.15. 1.15 times 10 to the minus 2. Okay, it's a silly mistake, but it's still a mistake. It's still wrong. What do we get there for EAs? Anybody have that? 4.9532 times 10 to the 7? And the units would be newtons per meter, right? Sorry, no, not newtons per meter. Newtons per coulombs. Thank you. No, EA would be a positive one because it's pointing to the right, right? Now, even if it was negative 10, we're not going to worry right now about making it a negative value. You could, and it would be okay if it was to the left. I usually don't worry about negative or positive till I go to actually add them up. That's when I look at my diagram and determine that. Okay, EB, almost the same thing, right? KQB over R squared. And the distance is the same because the point P is midway in between. I get 6.604 for that one. Times 10 to the 7 newtons per coulomb. Now let's add them up. the net field is equal to the field caused by A plus the field caused by B. Field caused by A is 4.9532 times 10 to the 7. Field caused by B, 6.6042 times 10 to the 7. Is that right? What's wrong? We got to make this one a negative. So in effect, we're subtracting there, right? Let's figure out what that is. I get negative 1.65 times 10 to the 7 newtons per coulomb. What does it tell you about the direction of that net field? To the left. We could have predicted that, right? This producer B, is a bigger charge. It's going to produce a bigger field given the same distance. So of course the net field is going to be to the left. It should end up being a negative value. Here's one of the questions I always get for this. Always get for this. Nobody's asked it yet, but probably somebody will before we're done this unit. Is point P a positive charge or a negative charge? What's the answer to that question? It's neither one. Hey, maybe there's a charge, maybe there's a positive there. Maybe there's a negative charge there. Maybe there's nothing there. Do you have to have a charge there to experience it just to have the field there? Remember, the gravitational field caused by the Earth is here no matter what. It's 9.81 whether we're here to experience it or not. Okay, the electric field is there whether there's a charge to experience it or what. So I don't care whether there's a positive there or a negative there. The field is the field. Now, if there was a positive there, it would be affected to the right and to the left. If there was a negative there, it would be affected opposite to the left and to the right as a result of B. But it doesn't really matter. Okay, you don't have to have the charge there to have the field. Look at the producer. Is it a positive or is it a negative? Does the field go away from it or towards it? Don't worry about if there's anything there to experience it or not. Odds are if you have three charges, if you actually had a charge there, you wouldn't be trying to find field. Odds are you'd be trying to find the force in that case, right? It would become one of those problems that you had on your quiz the other day. Right? Those are okay, right? A little bit different than what we did the other day, but really it's just a combination of what we did the other day with what we did yesterday. Let's try to see if we can get these two questions, and then we'll move on after we feel good about these, okay? It doesn't seem to be a whole lot of trouble with these two questions. We pointed out just a few minutes ago the diagram in question A. Here we've got two charges, A and B. We're trying to find the field strength to the left, not midway between them like we were in the example question, but to the left of charge A. It doesn't change anything except the direction of them is both to the left this time. Okay, the first one is away from positive charge A. The second one is away from positive charge B. Now let's draw the diagram for the second one as well, and then we'll leave it at that. Okay, we have an electron and a proton. Here's the electron, here's the proton. Okay, the electron is negative 1.6 times 10 to the minus 19, and the proton is positive 1.6 times 10 to the minus 19. We're trying to find the field strength midway between there again. Hey, the field caused by the electron, it's a negative. Pretend the proton's not there. Okay, the field points toward a negative electron. Okay, forget the electron now. Pretend it's not there. Which way does the field point caused by the proton? Well, it's positive, so it points away from it. The field points toward the electron, and the field points away from the proton, so they're both to the left. When we go to calculate these and add them up, we're going to make sure that we make them both positive, right? Is that okay? Okay, we're not going to do that one. I'm going to assign some questions for homework right now on page 553. Questions 1 to 9. And we're going to take a look at a few multiple choice questions here now as a group. Okay, so I'm not going to give you a chance to work on those at the moment. You might have a chance a little bit later on. Right now, I want to focus on these multiple choice questions. The first one being multiple choice number 44. Take a look at that one, please, and submit that one as multiple choice number 1, please. All right, let's take a look here, guys. I told you yesterday, I think that you're going to get a question like this on your test, right? It may be which of the following is a correct representation of electric fields. It may be a question like this where it says, what's charge X and what's charge Y? In the end, listen, if you know the shapes and you know the directions, you should be good here, okay? What do we know, first of all, before we look at our options about charge X and charge Y, based on the shape of the electric field surrounding it? Okay, forget about the directions, whatever. Let's just look at the shape. What do you know about X and Y based on the shape? Yep. They're going to be the same, right? Because the field lines are not joining up with each other. If they're opposite charges, the field lines are going to join up with each other. So they're both positive or they're both negative. Now, the direction of these field lines should tell you whether they're both positive or negative. Are they both positive or are they both negative? Based on the direction. Field lines are pointing towards both of those charges, right? Positive or negative? Negative. Field lines point toward the negative. So the answer for this one would be A, negative and negative. Got it? All right. Let's take a look now then at multiple choice number 46, please. Submit that one as multiple choice number 1, please. Okay, we've got responses from everybody here, almost all the people in the class. Every single person that's picked a response is picked B, toward the left of the page. How do we know it's B, toward the left of the page? Well, we've got a distance of 9 centimeters that separates this positive and the negative charge. That's irrelevant to the question, right? Because in the end, we're not trying to find a value of the field strength. We know the field caused by number 1 is going to go towards it. It's going to go toward the negative producer. The field caused by number 2, well, it's a positive producer. It's going to go away from it. If you have two fields, one to the left and another to the left, we don't need to know what the values are. We add those up, we're going to get a value that's to the left. So we've got an electric field that's to the left. Now, if one of them had have been to the right, which it's not, but if one of them had have been to the right, we would have had to have some numbers here, right? Do those completely cancel each other out? That depends on what the values of the producers are. Okay? We wouldn't know whether this was left or right, or 0, for that matter, without having some more numbers. Okay? Let's try another multiple choice question, please. Number 50. You can submit that one, please, as multiple choice 1 as well. Okay, take a look here, guys. Most people said D. A few people said B. Now, that means that everybody that submitted an answer here all recognize that it's going to be away from the alpha particle. That's good. The electric field always points away from a positive particle, and an alpha particle, you know from your data sheet, even though you don't really know what an alpha particle is, you know it's away from, you know it's a positive charge, so it's going to be away from it. That's good. Everybody recognize that. Now the issue is it D or is it B? Well, the electric field caused by the alpha particle, it is a producer, so it's going to be KQ over R squared. It's going to be 8.99 times 10 to the 9 times the charge of the alpha particle, 2 times the elementary charge on your data sheet, 3.2 times 10 to the minus 19. Okay, we divide that by the distance, 5.0 times 10 to the minus 11. Do that number, do that calculation, and I think what you're going to get here is, funny enough, 5.8 times 10 to the 11 newtons per coulomb, which is what only 2 of you said, versus 16 of you that said that. So, what have we done wrong? We didn't square it. Okay, if we square that, we're not going to get B. If we square it, we're going to get D, 1.2 times 10 to the 12. Don't you hate it when you make a silly little mistake like that, an easy mistake to make, one that all of us have made and probably will make, and they put the answer up there as an option? Okay, be careful with little things like that. Okay, be careful with little things like that, like forgetting to square that distance. D is the answer. All right, let's take a look at another one. 51. Ooh, we don't even have charges here. See what you can do on this one, okay? Multiple choice number 1 again, guys. Okay, guys, let's take a look here. The majority of people that submitted said C. No, the majority of people that submitted said D. But they were kind of all over the place on this one. We had people saying A, we had people saying C, and we had people saying E, option E. I don't know how to do this. This is a variable value changing question, right? The magnitude of an electric field a certain distance from a point charge, that point charge has got to be a producer because the field's not at the point charge, it's a distance away from the point charge. The original field, in other words, is kq over r squared, and the value of that field is 8.3 times 10 to the minus 4. My new electric field, this is the electric field after I make changes to it, still equal to k, but now q is a quarter what it was, so it's going to be 1/4 q, and then r, the distance, it says it's increased to 3 times what it was, so we're going to make it 3 times r. Don't forget to square the entire thing inside the brackets, not just the r. So it's not 3r squared, it's 3r squared. Let's pull the numbers out front here. 1/4 over 9, 1/4 over 9 because it's 3 squared, times kq over r squared. Okay, 1/4 over 9 is the same as saying 1 over 36 times kq over r squared. And we know the value of kq over r squared. It's the first thing we wrote down, 8.3 times 10 to the minus 4. I think when you divide 8.3 divided by 36, I think you end up getting d, 2.3 times 10 to the minus 5 newtons per coulomb. Make sense? How many people forgot to square the 3? Okay, hey, listen, if it's kq over r, well, then there's nothing to square, right? If it's kq over r squared, remember, you're not squaring r. You're squaring the distance, and the distance isn't r anymore, it's 3r. So you got to square that entire distance. Okay, remember, the equation isn't really kq over r squared. It's the constant times the charge divided by the distance squared, not r squared, distance squared. We just represented by r squared. Okay, now we're representing it by 3r squared. So it becomes 9 on the bottom. All right? My goodness, the multiple choice questions just seem to keep on going today. Let's take a look at number 52. This is the last one. Take a look at 52 here, please. And submit that as multiple choice number 1, please. All right, the vast majority of people that have submitted have said D. A couple people said C, and then a couple people said they weren't sure. So let's hope the answer is D, 0 newtons per coulomb. Honestly, when I look at this question, okay, the amount of numbers there are here and distances and directions and whatever, okay, my guess would be that things would cancel out. My guess would be that the answer would be D before I even do the question. But we don't know that for sure, so let's do the question. First of all, let's look at 3 and 4. Those look like the simplest ones to deal with right now. 3 and 4 are both the same charge, both positive. At point P, the field caused by 3 is going to be this way. The field caused by 4 is going to be this way. And since the same numbers involved, those are going to be equal and opposite. What do you know about those two fields if they're equal and opposite? They cancel. So there is no field to the left or to the right. Okay? It's as if these two guys weren't even here. Well, that simplifies things quite a bit because now we're dealing with a one-dimensional problem. The field caused by number 2, okay, it's going to be away from charge 2. Okay, number 2 is a positive producer. The field goes away from the positive producer. The field caused by number 1, well, it's a negative producer, so the field's going to go towards it. Now, which one's bigger? We're not sure. Okay, we're not sure here. So let's find the value of E1. Okay, the value of E1 is kq over r squared. It's 8.99 times 10 to the 9 times 12 times 10 to the minus 6. Don't forget the microcoulombs right there. Divided by the distance, which is 0.02 meters squared. What do we get for the value of E1? Does anybody have that? 2697. 0. Thank you. That would be newtons per coulomb, right? Let's calculate the value of E2 now. kq over r squared, but this time q is 3 times 10 to the minus 6. R is 1 meter. We do that math, and it also works out to be 26970. Well, if E1 is 26970 to the top of the page, and E2 is down the page, it's the same value. What do we know about those two fields? They also cancel each other out. So it's as if 2 and 1 aren't there either. What's the net field strength at point P? 0 newtons per coulomb. Yep. Can you divide the charge? Okay, be careful with that. Okay, be careful with that. Can you divide the charge by the distance? No. charge by the distance squared. Yes, but be very, very careful with that, okay? That only works if they happen to both be the same value. It'll tell you if they're the same value. So if you want to take a quick shortcut to see if they're the same value when they cancel out, yeah, that would work. The problem is, if they're not the same value, then you've got to use the K because it doesn't actually cancel out of the equation, right? That makes sense? So as a check, sure. And if you get lucky and they're the same value, great. If they're not the same value, well, then you got to go the full distance here, because what you found is not the electric field. It's the electric field not including the constant. Okay? All right, that's it for today, guys. Make sure you get your homework done. Page 553, courses number 1 to 9. And remember our quiz tomorrow on electric fields, okay?